Greeting, ladies and gentlemen. Today video we're gonna answering the 9th question. A torque of magnitude T equal to 4 kN is applied at end A of the composite shaft shown, knowing that the modulus of rigidity is 77 GPa for the steel and 27 GPa for the aluminium. Determine A, the maximum shearing stress in the steel core, B, the maximum shearing stress in the aluminium jacket, and C, angle of twist at A. We have a rod they made from composite shaft. They made by from composite shaft. The material, the first one will be steel and the aluminium. The core is steel and the outer will be aluminium. The aluminium rod is in the shape of hollow, which is you will have an outer diameter and you will have inner diameter. And for the steel core, it is solid shaft. So it been stated that this object will apply by torque. If 4 kN in magnitude, you will have a modulus of rigidity for the steel 77 GPa and the aluminium 27 GPa. Find out the maximum shearing stress for aluminium and steel and the angle of twist at A. So without any further ado, let's go to the problem solving. First thing first, we need to draw the FBD. I'm taking a point of view from here. If you take a point of view from here, there is a rod A to B, and the applied torque will be downward. If you take a look in this side, so the applied torque that will be downward, and the internal torque will be in a different direction, but have the same magnitude, which is P prime. I had made a few of problem solving before and finalize this problem solving, this solution. If I'm directly insert the value of 4 kN into this torsion formula, the elastic torsion formula, because we want to know what is the tau maximum. We were given 4 kN. I'm taught that the internal torque for aluminium, there will be this one. We know that C max and we can find out the value of J. But turns out when I make a finalized calculation for this equation, the answer was wrong. So that's why I make another reference and I find out this is the most convincing, and yet I'm still thinking why this equation was legit. But I know that somehow it will be logic, but yeah, I'm just thinking why. But anyway, this equation, the idea is the internal torque for the material shaft will be the summation of it that will be equal to the applied torque, which is in this case internal torque for aluminium plus by the internal torque for steel will be equal to 4 kN. So this is the equation. It is mean we cannot just take 4 kN slightly and include in the calculation and find out the tau maximum. So anyway, we make an analysis of aluminium. Since that we want to find out the maximum shearing stress, thus we will using elastic torsion formula. Tau maximum equal to torque prime refer to internal torque. C maximum refer, in this case there will be the outer radius over by J. Since that the steel, the aluminium were made from the hollow shaft, we will have an inner diameter, we will have an outer diameter, outer radius and inner radius. Outer radius or the outer diameter will bring you maximum shearing stress and strain. Meanwhile, the minimum shearing strain and stress will come from the radius, the inner radius or inner diameter. Since that we want to find out the tau maximum, that's why I'm using C max or C out, the radius for outer. So internal torque for aluminium times by the radius, the outer radius for the shaft over by Coulomb moment of inertia for hollow. So T prime for aluminium we don't know. C maximum there will be 0.0375 meter, come from the 75 millimeter, you divide by 2, you convert into meter, because we were dealing with a torque in SI unit 4 kN meter. The value of J, that will be polar moment of inertia. For the hollow shaft, for the hollow shape, there will be pi over by 2 C outer the power of 4 minus by C inner the power of 4. You know what the C outer, there will be 0.0375 meter. The C inner is come from 56 millimeter. You divide by 2, you convert into meter, you get 0.028 meter. You can calculate the polar moment of inertia, 2.14 times by 10 the power negative 6 meter the power of 4. You cannot solve this equation mathematically because you have to unknown torque prime and tau maximum, which is shear stress and internal torque. The internal torque for aluminium. So you mathematically you cannot solve this equation. You will need another equation to find out the value of T prime and decrease that equation. But if I tend to make this equation work out, you will need another equation that can relate to this relationship, which bring you to this equation. Phi aluminium, or angle of twist for aluminium, is equal to angle of twist for steel. There is the logic. If the steel and the aluminium were fixed together, when the torque were applied upon the object, there is no slip between steel and aluminium. It just makes sense to say, if the aluminium were twisted by 4 degrees, because there is no slip between steel and aluminium, the steel also will twisted 4 degrees. So that's why we have this relationship, phi aluminium equal to phi steel. And I'm derive another equation that will bring you to this relationship, which is length aluminium times by internal torque for aluminium over by polar moment of inertia for aluminium times by G aluminium equal to LS tau prime S JS over by GS. This equation is this is the derivative for this relationship. I think that you can make your own study, because for me, I can make it clear to see. I'm using three different equations, which is shear strain equal to C angle of twist over by length. I'm using another equation, the shear strain equal to tau maximum over by G, and I'm using tau maximum equal to T prime times by C over by J. Then I'm getting this equation. We will abuse this equation in this relationship. So that's why we will get LAL times by T prime AL and all of this stuff. So we need to classify what is the value that we know and we don't know. So when LAL and LS equal to 2.4 meter, the internal torque for aluminium you don't know, internal torque for the steel you don't know. The value of polar moment of inertia for AL we had just calculated just now, 2.14 times by 10 to the power of negative 6. The value for polar moment of inertia for steel you don't know, then you need to calculate later on. You know what is the modulus of rigidity for aluminium and the steel. So polar moment of inertia for steel, since that the shape for steel is in solid shaft, thus we were using pi over by 2 C the power of 4 equation. The value of C is 0.028. It's come from 56 over by 2. You convert into meter, thus you will get 0.028. Then you can calculate the polar moment of inertia for steel equal to 9.655 times by 10 the power of negative 7 meter the power of 4. So that you know all of the data, you can include it into this relationship. Then you will get internal torque for aluminium over by 2.14 times by 10 over the power of negative 6 times by 27 giga equal to internal torque for steel over by 9.655 times by 10 the power of negative 7 times by 77 giga. Since that the length for aluminium and steel were equal, you can just cancel out, and the value of giga in the below you can cancel out also. So you simplify this relationship furthermore, then you will get internal torque for aluminium equal to 0.777 to internal torque for steel. Thus, you can relate this equation with this equation. So, T prime S equal to 4K minus by T prime AL. You mix up with T prime AL equal to this stuff. Then you insert the data for you insert the value for T prime S. You will get 0.7772 times by 4K minus by internal torque for aluminium. You simplify even more. Thus, you will get T prime aluminium, that will be 1.749 kilonewton meter. Then finally, you can calculate the shear stress, because you know what is the torque prime for aluminium is. Then you will get this value, 13.65 megapascal for the shear stress for aluminium. Meanwhile, for the steel, we were using the same equation. We were using this equation. The internal torque for steel, the C, steel over by J. So, the internal torque for steel, we were using this equation. Since that we know what is the internal torque for aluminium, we can find out the internal torque for S by 4 kilonewton meter minus by internal torque for aluminium. So, there you can have it, 4 kilonewton minus by internal torque for aluminium, 1.749K times by the C maximum or the radius for solid, for the steel shaft, 56 mm divided by 2 convert into meter, you will get 0.028 over by it is polar moment of inertia, which is we had just calculated just now, this one. Then you simplify the equation, you will get 65.28 megapascal. It is close approximately to 65.26 megapascal. It may due to the leak in calculation, because in here you will have even more decimal places, but I'm just taking 3 of it. So maybe the value will leak from here. Maybe the value will leak from this value. So there is a lot of factor. But the point is, since that the difference between my answer and the schema were very close, so that's why I'm consider my answer is right. So 65.28 megapascal. For angle of twist, you can just directly use this equation. It is depend on you whether you want to use the angle of twist for aluminium or angle of twist for steel. It is because both of it have a same magnitude. In this case, I'm taking account aluminium angle of twist. So you will have internal torque for aluminium you times by the length for aluminium over by the modulus of rigidity times by polar moment of inertia for aluminium. 2.14 times by 10 to the power negative 6 is polar moment of inertia. 27 gigapascal is the modulus of rigidity for aluminium. 2.4 it is the length for the aluminium. So you solve this equation, thus you will get 1.749 K. No, there is the value for the internal torque for aluminium. Then you will get 0.073 rate angle of twist for aluminium. But since that you want to know in the form of degree, thus you need to convert it by times by 118 degree over by pi, you will get 4.16 degree. So I think that's all for this question. And again, if you know why you were using this equation, this relationship, internal torque for aluminium plus by internal torque for S equal to 4 kN/meter, why it is legit, I don't know. So I'm asking you, if you did know, please do tell me, because my logic saying that, why not? I'm just taking the internal torque for aluminium by 4 kN/meter. That is what my logic is. But turns out when I'm calculating by my own way, not getting into the answer, I make a reference and this is the relationship that they were using. So there is leave question in my mind. So if you did have an answer, please do tell me in the comment section. So I think that's all for today. Thank you for watching and have a nice day. Bye bye.